Greetings. In this video, I am going to begin to discuss loading. Very important subject. We're going to talk about live and dead loads, different load types. We're going to take our first look into free body diagrams and begin discussing lateral forces and loading possibilities for dealing with loading strategies for dealing with lateral forces. And then for our next presentation, we'll look into the world of dynamic forces. Okay, so there are different types of loading, and this goes to describing geometry and very important. So there's transverse loading to start off with. So forces applied perpendicularly to the longitudinal axis of a member. And after this section, actually, loading, we're going to start to get into our basic structural types, columns, beams, etc., and describing their longitudinal axes. So a beam's longitudinal axis runs in this direction, a column's longitudinal axis runs with it vertically, and here the transverse loading, it is getting the forces being applied perpendicularly to that axis. So that is the beam. The axis is here, and the perpendicular load is coming that way. If it were a column, which we'll see in the next slide, it would be a different situation. It would not be transverse loading. Okay? So transverse is describing the geometric relationship between the force and the beam. All right, causes the member or beam to bend and deflect. We talked in our last lecture about the different internal forces that the beam is experiencing. All right, now if we look at a column, we have axial loading, so applied in a collinear direction with the longitudinal axis of the member. So this is the axis, and the load, those two arrows, is running along with it in a linear fashion. All right, so it causes the member to stretch or shorten. So if this is a column, the arrows are pointing in, so it would be shortening. But you can imagine if we spun those columns around and we pulled on it, then we would be stretching the column, or we could say we would load a cable in that fashion. The cable could be pulled in that fashion. All right, so then we could also talk about the makeup of the load itself, and not just the geometry of it, but this is a uniform load. So a snow load is a good example of that. So here's our beam, here's our wall that the beam is fastened to. We're given some length of the beam, and then the uniform part would be all of these little arrows being the same length, and then this red line connects them all together, so that makes for a uniform snow load or some sort of uniform load on this cantilevered beam. All right, then we have a concentrated load. All right, so same situation, wall, beam, concentrated load. So this is a person standing out at the end of the diving board. Here we have a beam tying into a beam. So right here at this location on that beam, that is a concentrated load. Here's a column coming down mid-beam. So a concentrated load right there. So a specific location along a beam that's very small compared to the entire length of the beam. All right, so the mass hung by a rope, that would be similar to that. If that were a rope hanging there, same story. Triangular loads. Okay, so triangular load is a load that force varies linearly along the beam's length, 0 at one and a max at the other. So here's our cantilevered beam, and then we're 0 back here at this where it ties into the wall, and then our maximum load is here at the edge. And then snow again, we see a snowdrift making a situation like that. All right, so it's going from very small, and then the drift is created, and it's taller there. Another good classic example of that would be the weight against the foundation wall. So this is just a temporary wall for a construction project, but imagine it's your basement wall or any foundation wall for that matter. It's the same situation. So the loading is at 0 up here at the grass where we're standing. So if on the other side of this, let's pretend that if this is all weighted behind it with earth, then it's 0 at the top. And then as we go down and deeper into the earth, so this is grade where the grass is, where we stand up at outside our house. And then here's our basement wall, and then as we go deeper into the earth, the force increases on that wall. So it's 0 at grade, and then it goes to its maximum down here above the footing. All right, so that creates a triangular load. All right, now let's look at some, so we're kind of looking at some diagrams, so let's talk more about free body diagrams and what they specifically are. So it's also known as a force diagram. It's a pictorial device, often a rough working sketch used by engineers to analyze the forces and moments acting on a body. So again, the body is the beam or the column, one specific, it could be a cable, one specific member. And so here we have a beam, and this is a free body diagram, just a basic sketch. A whole series of such diagrams would be necessary to analyze a complex problem. So we're just breaking things apart one structural element at a time, essentially. All right, a graphic, dematerialized symbolic representation of the body in which all connecting pieces have been removed. So we've stripped away a lot of things. So this does actually show the supports. Typically, and we just had our presentation on a previous presentation, we talked more specifically about supports, or what types they are and what they do. So typically, these would be replaced in a free body diagram. This would just be an arrow, and this would just be an arrow as well. So that's a little more information. Part. So that's the connecting piece has all been removed. You would just leave an arrow behind. That's important. The type of connection is less so. Dematerialized, meaning we don't care if it's concrete, we don't care if it's steel or wood. We're just trying to figure out the geometry of the different loading types and how that kind of math all works out, like how these loads up above are getting to these supports down below, and basically how all that math works out. Each connection is replaced by a set of forces and moments that represent the action at the connection. All right, so we have our beam. We have 5 points along it. We have A at the end, B here, D here, C at the middle, and E at the end. We have 2 point loads coming down, concentrated loads, one at the end, point E, at end E, and we have point load at end A. So they're equal. They're both load P, so they're equal. And then here we have a uniform load stretching from point B or support 1, support B we could call it, and it extends in a uniform load all the way to point D, right there. Okay, so 2 different types. We have 3 loads, 2 point loads, and a uniform load in that one. We're given the length between, the distance between the supports, that's important, and we're giving the distance of the cantilevers, the distance A beyond the support. Okay, so we do want to begin to be able to read these pieces. All right. All right, so we isolate the structural element. We account for all the forces acting on it. We have the dead weight of the element itself. So we have not talked about that yet. We will shortly. And live loads acting on the element. And then reactions at the external forces. So those are all the pieces that are making this up. So here's an actual object. So here's a column, a light post, light column, light post, I guess. Here is the arm or the cantilevered beam that supports the light, and there's the light. So column, horizontal support, light, and that's pulling down. So 30-pound light pulling down, 3-foot beam, cantilevered beam, and then what is going on is basically what we want to look at is what is this light doing exactly. And I'm just going to change applications quickly. Okay, I am back. So let's just change our color. So we have a light post, we have the beam, and then we have the light itself. So the question is, what are these two doing exactly? What is that telling us? So this light is bearing down with 30 pounds of weight, and the effect, the action, let me do this in blue, the action is what kind of stress is this inducing on the system? What kind of stress is it inducing on the system? So it is making the system want to turn the beam in that direction, right? This is going down, so therefore this beam is being pulled down, and it is creating a moment or rotation about that point. That is the action. It is also, right, at this point, it is also, this beam is also pushing straight down. Straight down. So right at this location, there are two things occurring. It's wanting it to twist because the weight's out here, and it's wanting it to push down. So when we come back to the free body diagram, what we actually draw is the reaction. Reaction, right? And that's what this is. So this is the reaction. This is what is needed to keep the system in equilibrium. All right, so we have an action. The action is what this tends to want to produce, but then the reaction is pushing back up, and the reaction is spinning in the opposite direction, because ultimately this thing is not falling down, so it's in equilibrium. So I like to break it out, and so let me just do one more. So I'll just redraw that same one. So let's pretend we have a diving board. And here's a person standing on the diving board. And so they are a person who weighs 150 pounds, and they are on that diving board. And what that wants to produce, it wants to make this thing spin over, and it wants to push the diving board down. All right, those are two things that are occurring right at this location. The board is going down, and the board is wanting to spin. So those are the actions. I call them the actions. That's what wants to occur. And when we talk about free body diagrams, we are going to talk about we are going to draw in the reaction, and that is the pushing back up, and the counter moment, we might call it, is the opposite. Okay, so these things are what's keeping this situation in equilibrium. All right, these things are allowing, these reactions are allowing this 150 pounds to not cause a problem and not break the diving board. Okay. Okay. So let's just talk about some reading some basic free body diagrams, just see what information we could pull from here. So what type of load is present? So that would be a concentrated point load, point P. If the beam is 24 feet long, how far is the load from R2? So we have a point load coming down, we have a reaction, so this is reaction 1, so this is where this beam is being supported at reaction 1, and then it's being supported also at reaction 2, and this is right in the middle, because L is the length, and this is L divided by 2, and L divided by 2, so it is 12 and 12 feet. So the point load is 12 feet from reaction 2. Just again, a quick review of the different types that we discussed recently. So we have our rollers, then we have our pins and hinges are in that same group, and then we have fixed and simple supports. Okay, so we should be able to identify all of those. All right, so this is the circle that's kind of bound, where these rollers are more free to roll, literally and figuratively. Okay, so what type of load is present between supports A and B? So here's a support A, here's support B, no support there. I see a distance between A and B. I see a distance between B and C. I see a load coming down here, and I see a load pushing up there. All right, so type of load present between A and B, that is a uniform load from here to here. Equal arrows strung together, uniform load. What is the force of this load? We will describe this as 40 kN per meter. What is the force of that load? So it's 40 kilonewtons per meter. So the answer would be 40 kilonewtons per meter for 2 meters, or just 80 kilonewtons. All right. So this is not telling us that it's 40. It's not telling us that the entire answer is 40. It's telling us that it's 40 per meter. So it's 80. If this was 3, it'd be 120. What type of supports is the beam provided with? Roller and a pin. Okay. All right, what is the magnitude? So let's look what we see. We see a beam, I see a roller, I see a pin, I see numerous dimensions across the bottom. I see a uniform load here in the middle, a certain distance from A. This is just a center line there, and then I see a point load over here to the side as well. Okay, so what is the magnitude of the uniform load? So that is 690 newtons per meter for a length of 4.2 meters. So the answer is 690 times 4.2. So you'll either do the math in a quiz or that you'll look for that answer. But the answer is not simply 690. It's 690 times 4.2. Where's the point load located? The point load is located 2.9 meters from support B. Okay. I see 2 triangulated loads. They are greatest over the supports, and they come down to 0 in the middle, and that is right in the middle. I see 2 lengths from the supports to the center. What type of load is present? 2 triangulated loads. Where is the magnitude the greatest? Over the support. Where is the magnitude the least? Center span. Okay. All right, so that was free body diagrams and what loads look like on them. Now let's look at some different types of loads. All right, so primary consideration in any building design. Okay, so I kid sometimes when I teach these classes, structures classes, but basically if any questions on quizzes ask what is the the primary consideration, what is the source of kind of making decisions, like what is the deciding factor in our designs? It's basically either going to be loads or building codes, and we'll talk a lot about the relationship between those. But basically those are the 2 big things: loads, building codes, and spans are the big 3 primary considerations. They define the nature and the magnitude of hazard or external forces that are acting on buildings, and they tell us basically this is what we need to provide reasonable performance. So we have to resist these loads in order to make buildings perform correctly. All right, so we have building loads or forces. So we have 2 categories right off the bat. So we have gravity loads, things that are just weighing down, and then we have lateral loads that are coming in from the side. So lateral means to come in from the side, basically. Gravity loads are broken out into 2 different categories: dead loads and live loads. So dead loads are the weight of the building itself, and live loads are loads that change. So floor loads, so this would be people and furniture, basically anything that's not bolted down to a building. So anything that's bolted down, connected. So the furnace is a dead load, but the desk is not. All right, the desk is a live floor load. Roof loads would be snow, typically. Well, there's snow right there. So roof loads are typically snow. That's basically what that falls into. They don't support too much weight. There's wind load up there, but there's not too much other loads bearing down on roofs, typically. Okay, then lateral load. So coming in from the side, we have our wind load, and then we have an earthquake load, which is also a lateral load. And then we have loads, earth pressure, water pressure, blast, and impact, and we talked a little bit about some of those as well. Okay, so that is how we break it out into kind of a chart and branching it off into different categories. All right, loads are influenced by, influenced by what is being used inside of a building. So this kind of relates to code, essentially. When code is dictating how we have to design things, that's kind of talking about the occupancy and the function. Like Is it a high-rise office building with light intended uses where, it's desks and people, or is it a manufacturing facility? So that's where this comes in. Is it people? Is it stuff? Is it a parking garage? Okay. The configuration, so how big this building is, how it needs to hold itself up, and it needs to take care of all external loads as well. So the spans, essentially, joist spans, things like that will play a part of influencing the loads. And then the climate, where it lives. Is it a freezing climate? Is it a hurricane-prone climate, or is it something moderate in between the two? All right, so that all loads play a key factor in describing these things. And then they also play a very important part of making decisions. So after we've determined the loads, everything that the building is going to be experiencing, then we decide what materials are best, how these construction materials are being put together and fastened together, and then the overall architectural configuration. So a lot of things influence a lot of important decisions. Okay. All right. Any load. Load is a type of force exerted on an object. So it could be a gravitational or unrevealed force. It could be a pressure. So again, we discussed briefly, dead loads are basically things that are bolted down to the building. Concrete, steel, and glass. Live loads or probabilistic loads are things that come and go. So the amount of the load, when it arrives, how long it stays for, all those things could change. People, furniture, materials, that could all change. Materials, I would say, if they're bolted down, they belong to a dead load. So I'm not exactly sure what they mean by materials there. And then we have environmental or live loads. So people are live loads, but then we have another subcategory is environmental loads: wind, snow, rain, earthquake, and flood. Okay, so the reason for splitting loads into these categories is not always apparent. And in terms of actual load on an object, there is no difference between dead or alive. So the building doesn't care so much. Loads come and go, but, is it wind? Is it a person? Is it a boiler? Doesn't care so much. For the most part, these splits actually occur for safety calculations and making complex code models and studies, structural engineering models, studying them to make it all much more manageable. All right, so it's a little more academic why we break things up. Building codes provide acceptable live and dead load values and allowable deflection of floor and roof materials. So again, based on where this building is located, what's going on inside this building, how big this building is, all of that information is fed into the building codes, and then the building codes will tell us these floors could only support so much load. Or the building code would say, based on all that information, you have to design a floor that is capable of supporting. All right, that's how that would be said. The building code takes a lot of factors into consideration, and then it says you must provide a floor that could support this load, a roof that could support this load, a building that could withstand this much wind. Okay, so it provides the values. Those are the values. You must build to these values. And it tells you that your floor is allowed to deflect or bounce a little bit. All right, so in some situations, a little bit of movement's okay. And I talk about my old house quite a bit. So when I walk across my living room, there's a little deflection in the floor, and that's normal. It's an elastic load. It's there when I'm walking on it, but then when I get off, the floor bounces back and it's fine. And the building code will tell the engineers exactly how much little bit of bounce you're allowed to have. Okay? So that's how codes play part of that role. Okay, dead loads. This is the permanently installed parts. So roofs, floors, walls, foundations, claddings, finishes, fixed furniture, fixed equipment. So this is the easy part, really. All this stuff has already kind of been figured out, and pounds per square foot, it's all been determined. So once we figure out, again, where the building is, what type of building it is, then the designers will go and figure out how much those particular types of systems weigh. And then these numbers go into the dead load calculations. So this is not really, this is quite predictable. I mean, mistakes have been made, and obviously engineers and designers need to be diligent about these matters. But it's you shouldn't be reinventing the wheel typically. Most of this stuff has been worked out, and you can determine how much the building weighs. Okay. Okay, on the subject of what the building weighs and what it supports is the important idea of tributary area. So the area of the floor or roof supported by a member. All right, so here we see 9 columns supporting a floor, and basically this center column is supporting what is in red. So we take the space between these two columns, these two columns, these two columns, and we draw a line. Excuse me. Whatever's on this side of the line, this floor, is being supported by these columns. Whatever's here in the middle is being supported, whatever's between these two lines is being supported by these. And then we further go in this direction. So this center column is supporting the red zone. That is its tributary area. Okay. Here we see the solid lines are joists. So I see 1, 2, 3 joists are tied to this wall. These curved lines are just telling us that the drawing is kind of ending. There's another beam supporting them here. So this is a 20-foot joist running from here to here. So it's supported here and it's supported here. 20-foot joist, 20 foot, 20 foot. Now these two joists are 8 feet apart, and these two joists are 8 feet apart. Therefore, this joist is supporting these 4 feet. This 4 feet. 4 by 20. This joist is supporting this 4 feet. And likewise on this side, this joist is supporting this 4 feet and this 4 feet. So therefore, the tributary width that this beam is supporting is 20 feet by 4 and 4. So the answer is 8 feet wide by 20 feet long. So 160 square feet is the tributary area of that. Let me just jump into my, so this is my former sketch. Let me just draw one more. So beam, beam, beam. So just to explain this one more time, let's just say that this is 10 and this is 8. Therefore, this beam here is supporting 4 feet on this side and 5 feet on this side. So therefore, I just to go back to that example, 8 and 8 ends up with 8 feet in the middle. And that's just because they're all 8s. But in this case, if we had 8 and 10, we would have 4 and 5, and we would have a total of 9. And if this is 20 in length, then 20 times 9 gives us a tributary area of 180 square feet. All right, so that tributary area is that area right there, 9 feet by 20 feet. Okay. All right, and that's what we see there. Okay, just a few more slides, going through a couple other load types now. Okay, so wind produces. So now we're going to go through a couple different different load types. So wind produces non-static loads on structures at highly variable magnitudes. So the strength of the wind varies a lot, and it's non-static, meaning it changes. Okay, so very hard to predict. So here comes the wind. It's creating a pressure or suction inside, and it has complex effects on buildings. So failures can include uplift, taking the roof right off, racking the building, or just actually shearing or sliding the entire building. So now we're looking down on a floor plan. We have the wind coming in on this face of the building, creating a pressure right there. And then as it comes around the building on the far side, it actually creates a vacuum there. That's called the leeward side. The leeward. This is the windward side, and this is the leeward side. Okay. All right. So wind wants to knock buildings over, basically. All right. They vary substantially over the surface of a building. Wind loads are considered at two different scales. We have to think about them. So the loads produced on the overall building, so basically here comes the big wind load and it wants to knock this building over, and we have to keep the building from falling, and then we also have it at a local scale. All right, so the loads produced on the overall building, that's what we're looking at here. The main wind force resisting system includes shear walls, diaphragms that create lateral force resisting systems. So how to keep our building from falling over. We will circle back to that. Or we'll actually see that more in our next presentation. I'm just going to leave it at that. Yeah, we'll dig quite a bit deeper into that. But all these braces, that's what that's all about basically, is how this building wants to fall over. This is the short axis, the long axis, and it would want to fall over along that short axis. So how do we stiffen it up? All right, that's big scale. Now, if we could look at it on a smaller scale, we have pressures that are often greater on localized surface areas, particularly near abrupt changes in geometry, eaves, ridges, and corners. So this little building, this short little building, has no worries about being blown over completely, but the wind will damage it at more local conditions. So roof overhangs are very vulnerable areas. So wherever the geometry of a building changes, that's where wind could kind of grab onto the building and cause potential damage. Okay, and we will, as I said in our next presentation on loads, look more deeply into the vertical or the lateral force resisting systems. All right, so that's a little bit on wind. All right, fatigue strength. So the progressive and localized structural damage that occurs when a material is subjected to cyclical loading. I always think about the chair in IKEA that has that hydraulic pressing on it again and again to kind of show that you could stand up and sit down in this chair 1,000 times and it'll be just fine. That's cyclical loading, when things are happening again and again and again, and fatigue strength is what will fight that. And that's what that says. So it's repeated loading and unloading. So this is a wrench shown in cross section. So a wrench being used again and again and again. So microscopic cracks begin to form at the surface. So that would be happening right here. So the wrench is getting stressed. Eventually a crack will reach its critical size and then it completely fails. So that's what this is, an aluminum crank arm. So it's essentially a wrench. So the dark areas are where the slow crack growth occurred, and then the bright is where it fractured suddenly. So this goes back to our discussion of the stress strain curve, essentially. So right here, the damage was occurring permanently and slowly, but then it just, right at this point, it just snapped. All right, and then here is a model in a wind tunnel. So this would be a good example of cyclical loading. Not steady and regulated the way that the hydraulic press in the IKEA showroom is loading the chair. And this would not be, well, if this is in the hand of a human being, it would not be, cyclical loading like the hydraulic chair either. If it's a wrench in a hand, it varies. So it could either be uniform and cyclical, or it could be changing and cyclical. But wind bearing on a building could kind of cause a fatigue as well. All right, so the shape of the structure will significantly affect that fatigue life. So square holes and sharp corners lead to elevated local stresses. All right, so this is kind of interesting. So here we have these lines running through this structure are showing kind of how it's kind of showing if there are elevated local stresses. So right here, all these straight lines are flowing right through, no particular stresses. Here we've cut a circular hole, and now those forces have to move around it. Still, not the stress isn't as bad. Now we've put a square hole in it, and we could see elevated stresses beginning to occur at those corners where these lines are getting closer to each other. And then they cut this crazy triangular piece, and then you could see the elevated stresses are very, very kind of concentrated at that location. So the geometry of putting pieces together plays an important role. So round holes and smooth transitions or fillets are therefore important to increase the fatigue strength of the structure. So a fillet, that's a word in CAD when we join two lines, in steel work as well. So if this is two pieces of steel that are joined, that would be called a fillet weld. It's a weld, it's a fillet. The two pieces are being joined there. So that smooth surface is helping to reduce the stresses. Same way we could just weld this cylinder to this with this kind of abrupt change in geometry, but that would lead to increased stresses, where this is filleted and it decreases the level of those stresses. Okay, and now on to, so this is windborne debris and an impact load. So the capability of a material to withstand a suddenly applied impact load. I'm going to jump into a YouTube video here. So a space shuttle mock-up got hit by something. So that's let's just jump right into the video. 1 second. Okay, quick 1 minute video from I believe it's a window manufacturer. So I did work on a convention center in Cape May, actually, in New Jersey, right on the water, and it was the first time I was exposed to having to deal with hurricane force winds and build to those standards. Very different from building inland near Philadelphia, where I live. So window design and manufacturers finding windows that could withstand impact loads is very, very important.
During hurricanes and windstorms, windows must resist penetration by debris and remain intact in order to help preserve the integrity of the building. If the building envelope is breached through a broken window, wind may enter the building, causing an increase in pressure that could lift the roof and push the walls outward. Laminated glass helps to preserve the building envelope, keeping wind and other elements outside. During hurricanes and windstorms, windborne debris is common. So Cardinal tests finished window systems with laminated glass to verify that they stay intact and resist penetration. And because during these storms the windows may be subjected to sustained, gusting winds, both sides of impacted glass units are put through cycling tests that simulate winds up to 180 miles per hour. Cardinal also tests the security application of laminated glass for resistance to forced entry, and laminated glass cannot be cut from one side only, rendering glass cutters useless.
Okay, and that is actually a test, firing the 2x4 out of a cannon. So that's very, very specific, apples to apples tests that they have to do for all different window manufacturers to prove that your window meets a particular hurricane impact resistance, grading. All right, and then finally just snow loads, very simple. So for design purposes, snow is typically treated as a simple uniform gravity load on a horizontal surface. So it's typically pretty straightforward. It has caused some serious problems though, so it is potentially dangerous, but relatively straightforward in its calculations. Okay, so that covered quite a bit of material. We covered different types of loads. We differentiated between the dead and the live, and we got into free body diagrams. We're going to have to get used to looking at those, definitely. And next, we will get into the more complex world of dynamic forces. Okay, thank you very much.